or inconel alloys, stellite, hastelloy, titanium. Stainless steel to a certain degree is pretty tough to machine, especially the P660 grade. 304 is much more easier, 316 is even more difficult, but 660 is the most, it's frustrating to machine that. Also a new category of material called tungsten carbide, and any steel that is pre-hardened, which is above 45 HRC, can go all the way up to 65 HRC. Because the heat-resistant superalloy materials are metallurgically composed to have high strength at high temperatures, the stresses that are generated when machining are also very high. The unique capability of these nickel, iron, and cobalt-based superalloys to perform close to their melting points, and that's the reason those are used in those kind of applications where they are expected to perform at near melting point temperatures of their basic metal, give them varied, but they make very generally very poor machinability. They give a very poor machinability. Also, there was this concept that when you are machining the HRSA alloys, you would end up probably needing twice the amount of power on the machine that you would need to machine a similar part on steel. Now, although these alloys basically are ductile, their fatigue resistance, hardness, toughness at high temperatures combined to develop a number of wear mechanisms for the cutting tools. So the kind of wear that you see on a cutting tool is very high when you're trying to cut, especially titanium, inconel, stellite, and hastelloy. The wear is tremendous. The edge of the cutting tool is basically exposed to considerable mechanical stress, strain, and the heat while machining these alloys. There are also other forces that are acting on the cutting tool. For example, there is a high compressive and shearing force that act on the cutting edge while it's in the most vulnerable state. And as the chip flow temperature approaches the temperature at which the cutting tool material begins to lose its hardness, that's the vulnerable state where you can have chipping of the edges, or in some cases even disintegration of the tool. So if you look at the challenges, there are quite a lot of them. I've just noted down a few of these challenges because these are the most common ones. You have the chip thickness variation. I just talked about the stress induced by heat, and because they are ductile, their fatigue resistance is very high, they're hard, they're very tough. It also induces a very high tool wear, and there are some alloys that have the tendency to give a built-up edge on the tool. And most of these heat-resistant superalloys are having low thermal conductivity, which make it even more difficult for the machining process to proceed smoothly. Plus the fact that many of this HRSA, or the heat-resistant superalloys, they also work harden very quickly, and that gives rise to diffusion wear and usually leads to heavy burr formations. So work hardening can also hamper the subsequent process, or it could even hamper the subsequent cuts on that particular material. And on top of all this, the biggest challenge is how do you get your cutting conditions right for these materials. So we are going to talk about all these things in our few slides in the next hour. If you look at machining a particular part, for example, machining either inconel or titanium, there are certain things that influence the machining. For example, the state of the CNC machine itself influences greatly the cutting process. If you have a weak spindle, or if you have a machine with axes that are not strong enough or they're weak, it greatly influences the cutting time and the cutting of the part itself. The cutting tool and the tool holding are two important things in the entire process. So they greatly influence, one, the cutting time, and second, the cost needed to machine that particular part. So they also form a very crucial link in machining this particular process. Now, because the heat-resistant superalloys and even titanium have very poor thermal conductivity, the entire heat that's formed during the cutting process is actually passed on to the tool. And this can prove catastrophic if the heat changes or the heat is not dissipated, and for that, cooling becomes very crucial. So that also forms a very crucial part in the entire process. And then you have the fixtures or the vice or the holding vice that's actually holding the part together. The quality of holding greatly influences the parameters, or it also influences how quickly and how with minimal wear you could cut the part. If your holding is poor, you can't be aggressive in your cutting, so your time increases. If you're not aggressive in your cutting, the temperature increases. It doesn't drop, but it increases because you are going with a very low set of parameters. So basically, the entire process is affected, leaving you with lesser number of parts per tool. You could have disintegrations of tools also. So holding is also a very important aspect in the entire process. And then the most important thing here is the CAM system, because you could get other things right, but if you're not going to get your tool path right, then you're going to have major issues in cutting this part, whether it is titanium or inconel. So we are going to concentrate today on definitely the CAM system and also some other things related to this process that I've indicated today in the slide. Over the last few years, SolidCAM's iMachining has seen a lot of maturity in terms of development, in terms of usage around the world. And over the last couple of years, we have seen, or we have cut a lot of parts that are in titanium and inconel, and we have developed a lot of experience within the system to handle these parts effectively. So iMachining basically is a major revolution in CNC machining, where your cutting time could come down as much as 70% or even more. In cases of inconel, we have seen that the cutting time can be down as much as 98%. Or in cases of tungsten carbide, the cutting time could drop tremendously. I mean, we could go down to almost 96, 97%. So iMachining today is a major link between getting the part out right, getting the part out quickly, and getting the part out with minimal tool wear. So that is what iMachining does. If you look at iMachining as a technology, it has got iMachining 2D and iMachining 3D. iMachining 2D is more for prismatic parts, and iMachining 3D is also for prismatic, but also does a lot of 3D work, which is basically a transition from 2D, iMachining 2D. So in iMachining, what we have is we have increased productivity due to shorter cycles, where the time savings can be 70% or more. And because we do our own calculations of our cutting conditions, we dramatically increase the tool life because we take greater depth of cut, so the tool wear is uniform. We almost take the entire flute length as our depth, actual depth of cut, and then our radial engagement is then calculated to keep the force on the tool constant. So all these complex calculations are performed by iMachining inside SolidCAM. And because most of the calculations are done automatically, and they are done taking into account the machine capability, the material's physical properties, the tool definition, and the geometry, we have seen that harder the material gets or tougher the material gets, the performance of iMachining grows exponentially. So if your material is tough to cut, you can expect that iMachining will outperform any of your process and cut down your time by at least 70%, if not less. iMachining is also available on 4-axis and mill-turn. It has got a high programming productivity, which means the amount of steps or amount of time you spend to create a complex program to cut materials like titanium and Inconel is very less. You'll hardly take 3 or 4 steps to calculate a most complex toolpath for roughing and rough roughing inside iMachining. So your programming productivity jumps up tremendously. And because it's so easy to learn, it has got the shortest learning curve in the industry. Now, generating a toolpath is one, and getting the parameters to hold onto the toolpath is another thing. So iMachining uses what we call as a technology wizard, which provides optimal feeds and speeds, taking into account the toolpath, the stock, the tool, the material, as well as the machine specs. So it takes all of these into account to generate a envelope of cutting conditions that will drive the toolpath to cut the part. iMachining 3D is basically an extension of iMachining 2D. It's using the proven iMachining 2D algorithms and technology wizard algorithms, and provides you with a step-up principle to machine 3D parts using the same technology of iMachining 2D. So it gives you the same savings and sometimes more, because in 3D parts or in D parts, the savings are much more higher. So iMachining 3D, it optimizes machining of each Z step using the iMachining 2D technology. Rest material roughing is also done in those specific areas, but again, it uses a step-up principle. That means it goes to the deepest point first, uses the full flute length to remove material, and then moves in a step-up fashion to cut the areas only in the corners. And since it knows the stock very accurately, it does an intelligent localized machining, and it optimized ordering. No more retracts to the plane. It retracts straight away in 3D to the next point, and thereby it eliminates a lot of air cutting. And you combine iMachining 3D with our existing HSM and HSS solutions, you can actually completely finish a job in 3D very quickly. So there are 2 components in it. iMachining toolpath generator, which is the unique toolpath generator, and the wizard, which basically calculates the cutting conditions. Together is an ultimate solution for machining any kind of parts, be it titanium parts, be it Inconel parts, be it stainless steel, hard steel, or even soft materials like aluminum. Now, why iMachining came up was basically because the traditional fixed step-over kind of a toolpath would basically take a profile and just offset them together. Now, what this would happen, like what you're seeing out here in the picture, is that when the tool got into tight areas, especially the corners, the engagement of the tool was almost 180 degrees. Now, imagine this kind of an engagement on an Inconel material at a full flute length depth. The amount of mechanical stress and heat that's going to be generated is going to be so much that your tool will easily disintegrate even before trying to push into the corner. So what is the solution that came up for this was to reduce the depth of cuts, or instead of taking the full flute length as a depth, we would take only small shallow depth of cuts. Even after taking small shallow depth of cuts, we still had the problem in the corners. So what the operators used to do is to reduce the feed completely. So if you're going at, let's say, 2000 millimeters per minute, now you will feel that, or the operator feels that he cannot go at 2000 millimeters into the corners, so he cuts down the feed rates to about 700. Now he can't keep on doing that every time. So what operator used to do is just bring it down to 700 to cut the entire process. So in order to overcome those small areas, the entire process was slowed down. Now this is what is taken care easily inside iMachining. We have smooth tangential toolpaths, so there are no sudden changes in direction. Controlled stepovers. We don't overload the tool. We keep varying the engagement angle of the tool, and by doing that, we actually are keeping the force on the tool constant. If you go to any cutting tool manufacturer and ask the cutting tool technical person, what is your life of this particular end mill? And they will always come up with an answer. They'll tell you that the life of this tool is X minutes based on constant cutting force. So if your force is going to vary, your life of the tool is also going to vary dramatically. So if your force is constant, you can expect that your tool life will jump up substantially. It can go as high as 500% of the life suggested by the tool manufacturer. And then we have exact stock machining, wherein we don't cut air. We precisely know where stock is there, and we do exact stock machining. So all of them combined together gives you the intelligent toolpath that we talk about in iMachining. So the features of iMachining. We talked about so many things, so if I have to summarize the features of iMachining, the first one is it has a unique toolpath pattern. Now the toolpath pattern is unique, and it is unique to that particular given set of cut conditions. For example, I have a Makino machine. I'm cutting titanium. I'm using a 16 millimeter end mill with 45-degree helix with 4 flutes, and I have a pocket to be cut. So if any one of these 4 conditions change, iMachining's unique toolpath also changes because the condition. For example, I move from Makino to a local machine. Okay, so I know that now I have got less power on the spindle, I have got less RPM, I've got less feed rate, so my toolpath pattern cannot be the same like what it was for Makino. So it adapts itself to the new given cutting conditions or new conditions and creates another unique set of pattern of toolpath. So that is something that's with iMachining. It generates optimum cutting conditions. Sorry. There is a constant cutting force that is a result of the unique toolpath pattern and the cutting conditions. Both of them together give a constant cutting force on the tool. And because of the constant cutting tool, your tool life goes up. Another very important aspect of iMachining is its ability to predict vibration. Because iMachining knows what is the number of flutes that are present on the tool, what is the helix angle of the tool, and what is the geometry it is cutting, it is able to calculate how many points on the tool are in actual contact with the wall, and thereby figure out whether whole number, for example, 1, 2, 3 points are in contact, or you have got the decimals like 1.3, 1.5, or 2.3, 2.5 in contact. So based on this feedback, iMachining can actually predict if we are able to have vibrations or chatter in the cut. And it provides this feedback even before you actually take it to cutting, thereby giving a chance to the user to modify the cutting conditions. Either he changes the tool, or he uses a similar tool with more flutes or similar tool with lesser helix angle, till the time that he gets a very good feedback from iMachining saying that you're not going to have any chatter or vibrations in this particular cut. Now, iMachining comes up from this theory of Carl Solomon. It's a very old theory. It started in 1931 when he discovered that at a cutting speed of 5 to 10 times higher than the conventional machining, the chip temperature or interference temperature will start to decrease. Basically, what we are given to understand is that if I'll just make a drawing here. If we have got the VC on one line on the x-axis and the temperature in the y-axis, we are given to understand from the cutting tool vendors is that as your VC increases, my temperature goes up. So we are given to understand that we have a linear curve. But what Carl Solomon discovered was something different. He started increasing the VC, and he also noticed a similar thing of the temperature increasing. But at a certain point, when the VC was about 5 to 6 times or even 4 times, the temperature actually started stabilizing. It was not increasing any further. And after pushing the VC even further, he noticed that the actual temperature started dropping down. Okay? So that's like about 5 to 6 times of the conventional point. So if we draw a line from that and check here, so for a VC that was here, now we have gone here, which is about 5 times the conventional VC, and we are still achieving the same temperature. So a higher VC means I can achieve higher feed rates. Higher feed rates means I can cut the part much faster. However, the problem is also here with the higher VC. If you have higher VC and if you are engaging the tool into the material, that is a problem, because in today's systems, you really can't control the engagement into the material. Because if you say my engagement is certain amount of the tool diameter, then it will maintain the same thing even into the corner, where it's actually going to be very tight, and it's very difficult for the tool to cut at the same engagement in the corner, because it's going to have an engagement of the tool into the material of more than 180 degrees, and that could easily break the tool. So what our other competitive systems do is, in order to control it, they try to reduce the engagement and keep it minimum. Now that is also another problem, because if you keep engagement down to minimum, you're doing chip thinning. And when you're doing chip thinning, you're actually pushing up the temperature, edge temperature, much higher than what it would be. So you're actually again breaking or destroying the tool. So it's very important to understand that Solomon's theory is well applied inside iMachining, because it uses the principle to the core of what Solomon found out. Now, obviously the questions would be, how did Solomon achieve such a high VC? Because in 1931, there were no machines that could touch up that VC. The answer here is simple, because he was using a bandsaw. So he had this bandsaw cutters of a meter of width. So an RPM of even 400 or 500 meant that he could achieve a much higher VC, and he was cutting aluminum. So this theory was actually not accepted until quite recently, because even till today, some of the cutting tool manufacturers still don't take it that you can actually have a very high VC and still have lower cutting edge temperatures unless they see it actually happening in front of their eyes. So Solomon's theory is well implemented inside iMachining. Now, how does this theory work in practice? So we are talking about feed rates or parameters in the HSM range. For example, in titanium, the conventional range is between 60 to 75 or even 100, 110. But when you go into HSM range, it can go beyond 250, 300. Okay, so this is something very difficult to perceive or even to imagine that when you're cutting titanium, you could touch a VC of 200, 300 because the temperature we believe is high. But that's not the case with iMachining. Okay, that's because of this. Now this is the high-speed milling temperature balance. What happens when you move from conventional to high speed? When you increase speed from the conventional cutting to high speed machining, more heat is produced. Because more heat is produced, the temperature rises. Because the temperature rises, or because there's a rise in temperature, there's a gradual transition of the material or the stock to the plastic phase. So the material goes into the plastic phase. In this plastic phase, because it's in the plastic phase, the cutting forces are reduced because it doesn't need more force to cut the material because the material is already transitioned into a plastic phase. And there is less resistance to cut. And because there is less resistance to cut, there is less energy that is expended by the tool. This means that the heat produced is less and the temperature actually of the cut goes down. Now, if this process doesn't go into an equilibrium, which generally happens when you try to do conventional cutting using higher parameters, if it doesn't go into equilibrium, your next immediate reaction would be that your tool will disintegrate straight away because the temperature rises uncontrollably because you have no control over the process. However, with iMachining, after the temperature goes down, it immediately reaches the equilibrium state where the temperature stays in the lower side when it is cutting. So we avoid the collapse that generally happens when you try and reach higher cutting speeds. With iMachining, we'll reach the equilibrium within a couple of milliseconds. And how do we do that? How do we keep the force? How do we keep the temperature at a lower side? We do that by maintaining the cutting angle. What we do inside iMachining is we calculate from the physical properties of the material, from the machine characteristics, from the tool geometry, and the geometry to be cut, we calculate what should be the minimum and maximum engagement of this tool into the material. Based on this engagement, SolidCAM iMachining then takes into account what should be the feed rate at every point of engagement so that the force remains constant, which means if I have a lower engagement or a lower radial engagement into the material, and if I want to keep the force the same, I have to actually increase my feed. But if my radial engagement is more, then my force will eventually be higher if I keep the feed rate same. So in such cases, iMachining drops down the feed rate to such a point to keep the force on the tool constant. So If you look at the iMachining toolpaths, generally we use the morphing spirals. In morphing spirals, it can happen that your engagement can keep varying because when you're cutting parts in real world, you can't always get true spirals or equal cut everywhere. You have to morph between certain geometries. So when you're doing that, you can actually get more material on one side and less on the other. So in order to keep the force constant, iMachining varies its feed rate, and that feed rate variation depends on the engagement of the tool into the material. And by doing this, it's actually keeping the force equal on the tool. When the force is equal, the temperature is constant. When the temperature is constant, you get a much better machining, much better material removal with extremely low wear on the tool. So from the point of iMachining, we noted down that we have a very unique toolpath pattern. We create our own cutting conditions that includes feed, speeds, RPM, actual depth of cut, radial depth of cut, the engagement angle minimum and maximum. We also generate our own unique toolpath, and we also have this unique ability to predict vibrations even before you take the toolpath down to the machine for machining. However, beyond the toolpath, there are other peripherals that influence the superalloys machining. First of all, the first one that influences is cooling. The question is whether to use fluid or whether to use air. If you are going to use either one of them, how is going to be your cooling design? Because it's very important. Note that when you're using cooling, you have to have the cooling or the coolant hit the right spots on the tool. Because these difficult to cut materials, they create more heat during machining process than what steel generates when it's being cut. Titanium, for example, is a very poor conductor of heat, meaning that the heat generated while the cut, when it's being cut, does not dissipate quickly as it would do with steel. This poor conductivity combined with high hardness levels, which you can measure on the Rockwell scale, makes the cutting zone extremely hot, especially at the tool workpiece interface. Now, what this high heat does is, one, it can destroy the tool. Second, and most important thing, it could alter the dimensional stability of the material that is being cut. So to maintain this dimensional stability, to maintain low wear on the tool, you need to have proper cooling. And proper cooling means, first of all, what is the medium of cooling? And second, how are you going to design your cooling system? So these two areas are pretty crucial. The other critical element here is the cutting tool. What kind of a cutting tool do you use? Do you use a sharp corner cutting tool? Do you use a chamfered kind of a cutting tool? People talk about the chamfered edge, which generates lower forces and can be used effectively. Or you use tools with corner radius. So that is a choice that the user has to make. And I'm going to talk about that in the subsequent slides. The other thing is tool holding. How good is your tool holding? Because remember that when you're cutting these difficult to cut materials, and if you're using high helix cutters, these materials, they have a tendency to pull the tool out of your collet. Okay? So you have to use proper tool holding. It could be hydro grip, it could be power chuck, or it could be even shrink fit holders. But definitely not a collet, because a collet has a very small contact area and the tool can be pulled out even before you know it has started machining. So you can't use collet, hydrogrip, power chuck, or shrink fit. Work holding is also very important, whether you use a mechanical vise, a hydraulic vise, or a holding fixture. So you have to make this choice. Again, like I mentioned for collet, mechanical vise is a big no, because we know that the holding capability of a mechanical vise is much poor than a hydraulic vise. But of course, it's always better than a holding fixture, because a holding fixture sometimes is not as strong or stable as a vise. But if your design is such that vise cannot be used, then your holding fixture has to be such that you need to hold the part effectively. Because if the holding vibrates, or if there's a vibration during holding, it will unnecessarily create chatter. It can chip off the tool. So it's very important that your holding fixture is designed properly. Right, on the cooling, like I said, it is a very important topic because it plays a pivotal role in machining HRSA materials, the super alloys, titanium, and even stainless steel. We have seen that regular cooling on machines, the single nozzle cooling, is totally ineffective for machining such materials, because the dynamics of the cutting tool is such that the edge is changing. So the cooling has to hit it from every possible side. Now, how do we do it? One of the examples you can see is on the right side, a ring cooling design. Now, these pipes are available probably in your country. It will be available. If anybody is interested, they can get in touch with me, and I can give you this website where you get this modular structure with a pipe and a nozzle, so you can join them together to create a ring structure, and you can hit the cooling or the coolant, the fluid, directly on the cutting edge from every possible side. This is very important because the heat must dissipate from that point of that cutting edge. The second important thing here with cooling is the pressure. The regular machines don't have high pressure cooling. Now, this is something that I think you need to buy as an option, or sometimes it is available with the machine. But what we have seen is anything above 40 bar is needed when you're trying to machine these super alloys, because the pressure of coolant here is very important. It should wash away the chips, and it should cool down the tool subsequently. So the pressure here is very important. But if you're cutting steel, which is like 45 or 50 or 65 HRC, fluid cooling is a big no, because there the material itself is a good conductor. So the heat is there on the chip. So you should only remove the chip and not try to cool the tool, because the tool is already cooled, the workpiece is already cooled, the heat is there on the chip. If the heat is not removed, then it's going to pass off the heat back to the tool. In such case, when you're cutting steel, we recommend that you use high pressure air. Again, not from one side, but from several sides possible. Okay, so cooling, number one, very important. And one of the designs for cooling I've just shown you on the picture on the right hand side. If anybody again wants any information on this particular thing, they can get in touch with me. I'll give you the website, and you can find out if it's available in your country. From the cutting tool, what we have experienced is you should use a cutting tool with a maximum core diameter permissible. For example, if you have a pocket, and if you're trying to use a 10 diameter or 12 diameter, the chances of deflection are very high, especially when you're cutting titanium. In such case, if it is permissible, you can use diameter 16, because that reduces the deflection. You must use a tool with a corner radius. Sharp corner increases chipping. You can see on the right side, I've got an example from Sandvik where Inconel was cut using a chamfer tool and also with a tool with a radius. You can see that The tool life was more than double with a tool with radius as against a tool with chamfer, from 20 minutes to 52 minutes, and even the material removal was more than close to 3 times, from 27 centimeter cube to 73. And you can look at the pictures on the right side. The chamfer tool is actually chipped off on the edge, and there's a high wear also on the cutting edge. Whereas with the radius tool, the wear is very less. Now, you can also avoid the wear on the cutting edge by using a hone tool, because honing acts as a kind of an insulator when you're trying to cut materials like titanium and Inconel. The force distribution on a hone tool is much more equal, whereas with sharp tool, it's always acting on that point, and it's very vulnerable. So you get this chipping. You get this chipping that you're seeing here. But with a honed tool, with a very fine radius, it actually extends your tool life by almost 4 or 5 times. So as much as possible, try and use a honed tool. Tool holder, very important. You can see that we always suggest to use either a hydro grip, shrink fit, or a power chuck. What this basically does is it gives minimum run out. Now, there is a saying in Sandvik is that for every 10 microns that you add to the run out, you actually are decreasing the tool life by almost 50%. Cutting stability also increases the amount of depth of cut that you take. If your cut is very stable, you can actually go faster, you can go deeper. So holding becomes very crucial. And hydro grip, shrink fit, and power chuck, they have got very high clamping forces. And also the amount of area that is being held of the tool is also pretty, it's more than 2 times the diameter. So the holding area also is very high. So what it basically does is it prevents the pullout of high helix cutters, especially for iMachining kind of tool paths where it's machining really fast. From the software perspective, the feed rate control is very important. Generally, when you use a conventional tool path, okay, you apply a feed rate, and that feed rate is valid for the center of the tool. But imagine the tool turning over on an internal corner. The amount of turn that it takes on the center of the tool is very small, but the periphery of the tool that is actually cutting the corner is going to turn at a very high speed. So what is going to happen is, if you keep the feed constant, it is actually going to eat away into the material more. That means your chip thickness is going to increase dramatically into the corners, and that's where you hear that great noise when it turns into a corner. So the answer here is that you need to cut down on the feed rate. Now, if you go back into iMachining, in iMachining you have got a separate area where you can actually control the chip thickness for arcs, and you have a slider. If you keep the slider at 100%, it means that iMachining will maintain constant chip thickness even when it is going into the corner. Your time will slightly increase because it's actually reducing its feed rate into the corner to keep the chip thickness constant, because it knows that the periphery is cutting and it needs to move the periphery on a very small area very quickly. So it drops down the feed rate. If you move the arc, or if you move the slider to 0, it means that the feed rate will be kept constant between G1 and G2. It will not drop down the feed rate. What this will do basically is it will increase the chip thickness on the corners. This can reduce your time, but it will also add great stress on the tool. So your tool life can drop down. So what we suggest in iMachining for super alloys is that the slider must be kept always at 100% in order to maintain constant cutting force even in the corners. Right. We come Next, to a very important subject, a subject that's very close to me because a lot of things we have done in this area, and that is the machinability of a material. Why is this so important? Because we always had complaints from customers about tool life. When we said a tool life can be as high as 400%, some of my customers never got it. So we investigated what was going inside. And we realized that when we define the material inside iMachining, we define the ultimate tensile strength that's given to the customer by the material manufacturer. It comes as a test chart, and they have this particular value. Sometimes this is not a very accurate representation of the material. Okay, so it is important that we determine the machinability of the material. It can be determined by several methods, but we have found a very easy and important easy method in determining the machinability of a material. Now, first of all, we need to understand what is machinability. It's basically a term that indicates how a work material responds to the cutting process. In most general cases, a good machinability means the material is very easy to cut. You get a pretty good surface finish. You have a very nice or a very high tool life, low power requirements on the spindle. The total cost of cutting is also lower. But you have got several definitions of machinability, and there's also something called as a machinability index, which is basically a KM that equals, or the machinability index equals to the cutting speed of the target material, which ensures a cutting life of 60 minutes, divided by cutting speed of a reference material that ensures the life of 60 minutes. It's a bit confusing, so I'm going to explain it into a next slide on how these two terms are defined. If the machinability index is more than 1, it indicates that the target material is much easier or has got a much better machinability than the reference material, and vice versa. So if it's less than 1, it has a poor machinability. If it's more than 1, it has a good machinability. So let's start with the AISI 1112 steel, which has index of 1. So this is our reference. So machining this steel at a cutting speed of 0.5 meters per second gives a tool life of 60 minutes. So here my V60R is 0.5 meters per second. So the machinability index for SS302 or stainless steel 302 is 0.23, where 0.23 is basically the V60, or it's the cutting speed of the target material, which ensures a life of 60 minutes. So SS302, when cut at 0.23 meters per second, gives a tool life of 60 minutes. So if I calculate on this formula, I get a machinability index of 0.46. So 0.46 is obviously less than 1, which means that SS302 has got a poor machinability when you compare with the AISI 1112 steel. The AISI 1045 is also the similar one. It has a cutting speed of 0.36 meters per second to give you a 60-minute tool life. So that brings the machinability index to 0.72, which is better than SS302, but it is still lower than the AISI 1112, this regular steel. So the order of machinability here is 1112, 1045, and SS302. However, like I said, this is all theory, because in the end, we need to determine machinability on our shop floor, giving all the existing conditions. But why is machinability so important? First of all, if you get the right machinability of the material, it improves your tool life dramatically, and we have seen this at several customers. It allows iMachining to determine almost near perfect cutting conditions for that particular given set of machine, material, tool, and workpiece. You get a much better surface quality, and in case you're machining materials that induce a lot of warpage, you actually reduce the chances of getting warpage on that material tremendously. Believe me, this has been our experience, and overall there's a process improvement. However, apart from the machinability index, which is a theory, there are several factors that actually affect machinability in real-world conditions. The physical properties of the material, the structure, the microstructure, mechanical strength, hardness, hot hardness, hot strength, work hardenability, thermal conductivity, chemical reactivity, stickiness, and self-repeat. All these things one cannot define in a software, because then it becomes too complex a process to define everything to determine my cutting conditions. The cutting tool influences the machinability, the process influences the machinability, and the environment itself, the fluid, the holding, everything is actually influencing the machinability. So how does one calculate machinability? For that, I'm going to show you a small test inside iMachining that you can do within 5 minutes to generate a machinability chart for that particular material. So all you need is a simple block, which is 100 by 75 by 50. Now this block should be from the same batch of material for which you would like to create, or you would like to have the machinability index. For example, I'm going to use a block of ASI 1045 steel to determine the machinability of that batch of material. I'm going to use a Mazak FJV with a 10 kilowatt continuous spindle power, and I'm going to use a 12 diameter end mill, and our theoretical cutting depth, or the actual depth, is about 24. So what we have here is a model where we are going to cut about 10 millimeters on every side. That's all we need to do. So that's why I said the process takes about 4 to 5 minutes. So what we have, when we start with iMachining, we need to define the material. So I've defined a ASI 1045 material, and I've picked up the ultimate tensile strength, in this case from MatWeb, and that is 515 megapascals. So enter 515 megapascals as my material, and I generate a 2D iMachining toolpath for that particular step. But here, remember that I'm not going to a depth of 24 millimeters. I go to a depth to such an extent that I get an ACP, or the actual contact point, as a whole number. Why I do this is because I do not want to induce any kind of chatter into this cut or vibrations, because that will again change the machinability index. It might not give me the right value. So I must ensure that I don't have any vibration or chatter in this cut. So I'm not going to go to 24, but I found out that at 19 millimeters I get 2 as my contact point, because I'm using a 12 diameter tool, 4 flutes, and a 45-degree helix, and that at 19 millimeter depth of cut gives me 2 as the ACP. And we are also going to keep our machining level at level 8, because I need some feedback from iMachining, which I'm going to compare it with the real world. In my cutting conditions, when I go inside, I can see here that the power required for this particular cut at level 8 is going to be about 5.2 kilowatt. So I capture the screen because I want to note down all these parameters. So I capture the screen and the power required. I generate the toolpath and take this G-code to the machine. Once this is on the machine, I start cutting the part. And after about 2 passes, because sometimes you can have the stock may not be uniform, so we allow 1 or 2 passes to go. And after 2 passes, I start looking at the control to look at the spindle load. Now, because it's a morphing spiral, and we have said that it generates a constant cutting force, my spindle load is going to be near constant once it is engaging completely on all four sides. And I observe in this case that my spindle load meter is showing 60%, which means that out of 10 kilowatt, it is using 6 kilowatt. However, if you note that our iMachining had generated a figure of 5.2 kilowatt, whereas on the machine, I'm getting 6 kilowatt, which means this batch of material that has come to me is having a machinability slightly poor than what was defined by MatWeb as 515 megapascal. So I now need to figure out the machinability index for this particular batch of material. So it's slightly tougher than the material that we have chosen. So what do? Is I go back into the material database and I push down the machining factor to about 16%. You could put it at 12%, go back and come back again. But in this case, I pushed it to 16%, minus 16%. And I go back to my toolpath, I edit it, but I make sure that I enter these three values from the screenshot I had saved earlier, especially the maximum chip thickness, the maximum VC, and the maximum cutting angle. Once I enter these three values from that screen, I notice that I'm getting a power requirement as 6 kilowatt, which means the material that's there of that particular batch of material that has come in, that has got a machinability which is about 16% more tougher than the material that we chose from MatWeb. So by arriving at this particular machinability, I can ensure that I'm going to have very good tool life. I'm going to get exact cutting conditions determined by iMachining, and overall my process is going to be very smooth, and I'm going to have much lower time of cutting for that particular material when you compare it to the conventional process. So this is very important, and there's, however, a small disclaimer that this particular machinability test doesn't work, or we've not seen good results for extremely soft materials like copper or softer than copper. But anyway, we are not much bothered on those very soft materials because we're talking of hard materials, and we have seen this test work 100%. It's 100% accurate for hard materials, for steel, for titanium, for Inconel, or even for aluminum. It works very nicely. So the machinability is very important, and you have to have this ready before you start iMachining. Okay. Another very important question arises, and this I've seen mainly this question come from different machine tool manufacturers, because I've heard them tell to my customers, or probably some of them have told you, or probably you have had this doubts that iMachining generates such high parameters. It generates very high VC, it generates high actual depth of cuts, it generates very high feed rates for machining. Will it really affect the machine? Will it affect my axis? Will it affect my spindle? Because these are some of the fears that are instilled into the minds of users by the machine tool vendors, people who really don't understand the concept of iMachining. So what we did was we did a force calculation when iMachining is cutting, and we did a real-world test. The iMachining toolpath, we all know it's combined with optimum cutting conditions provided by the technology wizard. They ensure constant load on the machine, on the tool at any given situation. And if you really are using iMachining, you would have noticed that on the spindle meter, the load doesn't go beyond 17 to 20%. Some cases it can go as high as 30%. Okay, so depending on what level you're using. Homley in Germany conducted a test with several CAM systems because they were having a problem with load on their spindle. And what they realized was iMachining, or with iMachining, the forces acting on the spindle are the smallest of all the CAM systems that use the high-speed machining techniques. Makino also tested the same on their A55 and A61 and reached similar conclusions. Now, this can be a good sales talk. I can say Hermle did that, Makino did this, but unless and until I don't show you hard data, it's very difficult for anybody to accept this whole fact. So we did a force measurement with a university in Czech Republic, and this particular university is equipped with dynamometers. They're a very expensive piece of equipment. So they are equipped with rotational dynamometers for cutting force measurement, axial dynamometer, and workpiece dynamometer. And you have a rotational dynamometer which is mounted on the spindle, and this measures forces in all directions and also the torque. And then you have the axial dynamometer. It's meant for drilling and turning operations. And you have got the workpiece dynamometer, which is meant for measuring force when cutting in all directions. And the whole thing was measured using a software called LabVIEW. The entire readings were taken through shielded wire and fed to LabVIEW almost dynamically. We had the sample part. It was an aluminum part and 8mm diameter cutter with 30mm depth of cut and a helix angle of 38, and we used iMachining level 5, which is a moderate level. And in the classical pocketing strategies, that is the regular pocketing, we used, when we cut the part using the regular pocketing, we had a depth of cut of 4mm, a side step of 7.2mm, and a feet per tooth of 0.09. This was the force. The force at 4mm was almost close to 450 newtons when it was cutting. Whereas the yellow is the ramping force and green is the machining force. So the force here at 4mm depth of cut in aluminum using the conventional cutting strategy was about 450 newtons. Using iMachining level 5 at 30mm depth of cut and a VC of 283, the force was less than 300 newtons. What this basically tells us is that the force acting on iMachining at about 8 times the depth of cut and almost 2 or 3 times the parameters suggested by the regular cutting tool is less than 70% of the force that is actually acting at 4mm depth of cut. So iMachining actually produces the lowest cutting forces or the lowest forces acting on the spindle, acting on the tool, and also on all the axes. This has been already established, well established using this experiment. Right. We also did very interesting trials at Kennametal in India, where we tested high-speed machining of titanium and stainless steel by using iMachining on Kennametal's Harvey cutters, 12 diameter and 16 diameter, and the blocks, the TIAL6V was supplied by a major aerospace company. And we did a periphery and pocket machining on a Mazaka FJV200. On a stainless steel P666 trials, this was the part, 250 by 200 by 60, and these were the results. 16 diameter R3 bullnose, VC of 171. That was the moderate level or intermediate level of 4, where at level 8 it would be as high as 280. So we used the 171 at level 4, and finishing also we used level 6. That's about 205 VC. The cycle time for cutting this was 3 minutes 36 seconds. The conventional cycle time was about 25 minutes. Pocket machining, again we used the same 16R3 bullnose cutter, and finishing also we did it with the same cutter, and our cycle time was 4 minutes 48 seconds. In all of these, the load on the spindle was hardly 20% and not more than that. And then we have the titanium machining. Again, similar block size. First, we used the periphery. We generated the tool path with a 16R3 bullnose tool, depth of cut of 20 millimeters. Level 4, that's, I would say, the intermediate level, cycle time of 3 minutes, 18 seconds. The pocket was done with 16R3 and also with 12 diameter cutter. And the cycle time was 4 minutes, 42 seconds with a spindle load of 20%. And we again roughed out an internal pocket with a 12 diameter end mill, 12R.8, and a depth of cut of 17 millimeters. Roughing and finishing together was 3 minutes, 58 seconds. However, the goal here was not to find whether it is fast or not, because Kennametal is already convinced that we are very fast in cutting steel and other materials. The goal here was to find out the tool life. And after cutting 6 such parts, we took out the tool and we started to check for the wear on the 12R.8 tool. After 6 parts, Kennametal at 20x magnification noticed that there was a 0.1 millimeter wear on all the cutting edges uniformly. So this is a major leap ahead, because they were expecting a much higher wear on the tool. In fact, they were expecting that the tool would last only 3 parts, but after 6 parts at 20x magnification, they still have about 0.1 wear, which is a dramatically great improvement in tool life. Another customer of ours in Israel, where we had this material in titanium, their standard cutting time was 17 minutes. With iMachining 2D, it was down to 3.5 minutes. That's like 80%. I've told you in the beginning, a minimum of 70% and above. So a total time they saved was 16 hours for 75 parts. That's almost equivalent to 2 shifts. So you cut down on the time required on the machine by 2 shifts. That's a big, big saving. Another trials we did in India on Inconel on a Herco VMX 60, where we used the cutting at level 4 of SolidCAM. Level 4, that's the intermediate. And the VCV was almost 81. That was almost twice of what ISCAR suggested. And our tool life that we achieved was 86 minutes against the estimate of ISCAR of 26 minutes for that particular tool. So our tool life was dramatically up by 3 times. Another company in the US on Inconel 625, the machining time savings was 75. Now these are some of these stories. There are tons and tons of others, but I've just picked out some that I could show you in this particular webinar. Klein Oilfield on Inconel 625, the time savings was 86%. More important, the tool life up by about 500%. So a lot of nice things are happening. But the icing on the cake has to be the last success story, and this was done on tungsten carbide. It's a 50 by 50 part, and this had to be roughed out using diamond-coated cutters, special cutters. The company was cutting that particular part in about 42 hours, breaking 9 tools. So every part they had to change 9 tools. iMachining did the same part in 54 minutes using just 1 tool. So apart from cutting down the cutting time by almost 95–96%, we also saved on the amount of money that is spent on buying cutting tools. So we also saved that much. So it adds together, it's a big saving. So summary, iMachining coupled with the right cutting tool, the right cooling and cooling design, the right holding, and the machine can easily cut any given material, including titanium, Inconels, stainless steel, hard steel, tungsten carbide. You give the material, and iMachining would be more than glad to help you to cut the part easily with a higher tool life and a lower machining time, resulting in a productivity of almost 70% or more. Thank you very much for patiently listening for this webinar, and if you have any questions, I would be more than glad to answer your questions.
Okay, Ahmad, I see we have a couple of questions. We are a little short in time, so I will read it quickly. The first one is, how does iMachining cope with interrupted cuts that only occur at the tooltip? For example, a part that has a half hole across the floor of the component.
Okay. Honestly, if you can get that particular geometry also into your part geometry, because we assume that the part geometry is closed, but if you're going to have holes in between, that's going to create the interrupted cuts. In such cases, you also need to model those holes in the geometry. In such cases, the system will try and take care, although not 100%, but it will try and take care not to jump or not to go through the cut onto the holes. It will try and do some maneuvers around the hole. But like I said again, it's not 100%. It may not work at all at 100% of cases, but in some cases it definitely works, provided you have that in your geometry also. Believe is there any restriction in the ratio of tool length to diameter? For example, you use diameter 10 tool with flute length of 70. Could I use iMachining with that? Oh yes, very much. If you look at iMachining's wizard, or from the last couple of versions, you might have noticed a very subtle change, that when you have a tool with out of folder length of more than, I think, 4 or 5, iMachining changes its conditions a bit inside. In fact, if you go to YouTube, there are a couple of videos where a 16 millimeter tool has cut at a depth of about 78 millimeters. So you have got one full tool cutting at 78 millimeters. So it is very much possible, provided, again, here, the holding of the tool is very important. You could not be holding this tool in a collet. You should be holding it either in a shrink fit or a hydro grip, because the tool run out here is going to be very crucial.
Okay, Ahmad, I think this is it for now. Thank you very much for this very interesting presentation, and thank you everyone for joining us. The recording of